Welcome to the fascinating world of construction materials. In this series, we'll explore the very substances that shape the buildings around us, and our journey begins with one of the most versatile and ancient materials used in construction, gypsum. Gypsum, a mineral composed of calcium sulfate dihydrate, has been a cornerstone in construction for thousands of years. From the majestic pyramids of Egypt to the plaster walls in modern homes, gypsum's adaptability and essential properties make it a material worth knowing. So, join us as we uncover the history, production, and applications of this remarkable material. Whether you're a seasoned professional or just curious about what holds our world together, there's something here for everyone. Let's start. Gypsum is a soft sulfate mineral composed of calcium sulfate dihydrate. The name gypsum is derived from the Greek word gypsos, which means plaster or chalk. Gypsum is a naturally occurring mineral that humans have utilized for thousands of years across various areas, including construction, agriculture, and even the arts. It's one of the most widely used minerals in the world. Known for its softness and can be easily scratched with a fingernail, its physical appearance can vary from transparent and colorless to white, gray, brown, or even pink, depending on impurities present in the mineral. Gypsum's chemical composition is relatively simple, consisting primarily of calcium, sulfur, oxygen, and hydrogen atoms. Its chemical formula indicates that each unit of gypsum is composed of one calcium atom, one sulfur atom, 4 oxygen atoms, and 2 water molecules. The 2 water molecules are structurally bound to the calcium sulfate, giving gypsum its characteristic hydrated form. The water content in gypsum is essential to its unique properties and versatility. When gypsum is heated, it undergoes a process called calcination, during which it loses some or all of its water content, depending on the temperature and duration of heating. This results in the formation of different gypsum products with varying properties, such as plaster of Paris, stucco, and gypsum board. Chemical properties. Gypsum, a naturally occurring mineral with the chemical formula, exhibits several important chemical properties that contribute to its versatility and usefulness in various applications. Here are some key chemical properties of gypsum. Hydrated structure. Gypsum is a hydrated mineral, meaning it contains water molecules within its crystalline structure. Specifically, each unit of gypsum contains 2 water molecules chemically bound to the calcium sulfate ions. This hydrated structure is crucial to its properties and applications. Dehydration. One of the most notable chemical properties of gypsum is its ability to undergo controlled dehydration when heated. When gypsum is subjected to heat, typically at temperatures ranging from 150 degrees Celsius to 190 degrees C, it loses some or all of its water content. This process is called calcination. The degree of dehydration depends on the temperature and duration of heating. Partial dehydration. When gypsum is partially dehydrated, it forms a material known as plaster of Paris or calcined gypsum. Plaster of Paris is a white, powdery substance that can be mixed with water to create a workable plaster paste, used in various construction and artistic applications. Complete dehydration. If gypsum is heated to higher temperatures and for an extended period, it loses all its water content, transforming into anhydrous calcium sulfate, commonly known as anhydrite. Anhydrite has different properties compared to gypsum and is less commonly used in construction. Rehydration. One of gypsum's unique properties is its ability to reabsorb water and return to its original hydrated form when it comes into contact with moisture. This rehydration property is exploited in the production of gypsum-based construction materials like drywall. When drywall is exposed to moisture, it can absorb water, which helps to resist fire and provide a protective barrier. Chemical stability. Gypsum is chemically stable under normal conditions, but can slowly dissolve in water over time. This property makes it suitable for agricultural applications, where it can be used to provide essential calcium and sulfur nutrients to plants. Gypsum can also improve soil structure by displacing sodium ions in sodic soils. Chemical impurities. While the chemical formula for gypsum is relatively simple, natural gypsum deposits may contain impurities, including small amounts of other minerals or elements. These impurities can affect the mineral's color, purity, and suitability for specific applications. In summary, gypsum's chemical properties, including its hydrated structure, ability to undergo controlled dehydration and rehydration, and chemical stability, make it a versatile mineral used in various industries, from construction and agriculture to art and industry. Its capacity to transform from a hydrated to an anhydrous state and back again is particularly valuable in many practical applications. Geological occurrence. Sedimentary deposits. Found in sedimentary rocks, gypsum forms from the evaporation of water in ancient seas, lakes, or other bodies of water alongside other evaporite minerals like halite and anhydrite. Desert environments. In arid regions, high evaporation rates and groundwater carrying dissolved calcium and sulfate ions lead to the precipitation of gypsum crystals on the surface. Cave deposits. Gypsum can also form in caves through speleogenesis, where groundwater containing dissolved gypsum interacts with the cave environment, creating formations known as gypsum flowers or selenite. The formation of gypsum involves a sequence of geological and environmental processes. Deposition. Gypsum initially forms as dissolved calcium and sulfate ions in water. These ions can come from a variety of sources, including the dissolution of calcium-containing minerals in rocks and the leaching of sulfur compounds from organic matter and volcanic emissions. Evaporation. In environments with high evaporation rates, such as arid regions or evaporating ancient seas, the water becomes concentrated with dissolved calcium and sulfate ions as it slowly evaporates. This increased concentration of ions makes it more likely for gypsum to precipitate and crystallize out of the solution. Crystallization. As the concentration of calcium and sulfate ions continues to increase, gypsum crystals begin to form. These crystals may grow over time, eventually accumulating in layers or beds within sedimentary rocks or depositing as distinct crystals in caves or other underground environments. Alteration. Over geological time, gypsum may undergo alteration processes, such as hydration and dehydration, depending on changes in temperature, pressure, and the presence of other minerals. These processes can lead to the conversion of gypsum into anhydrite or other minerals. Gypsum deposits can vary in size and purity, and they are often associated with other minerals and rock formations. The specific conditions under which gypsum forms, as well as the geological history of the region, determine the characteristics of gypsum deposits found in different locations around the world. Overall, gypsum's occurrence and formation are closely linked to geological processes and environmental factors, resulting in the wide distribution of this mineral in various geological settings. Thank you for watching. If you found this information helpful, don't forget to like, share, and subscribe. Stay tuned for more insightful content. Take care and see you in the next video.